Welcome to Nuke Engineering. Are you preparing for a structural engineering interview and wondering what kind of technical questions you might face? Welcome to this video on Common Structural Analysis Interview Q&A, your quick and practical guide to cracking structural engineering interviews with confidence. Whether you're a fresh graduate stepping into the industry or an experienced engineer brushing up on fundamentals, structural analysis is one of the most critical topics interviewers focus on. From understanding load paths and bending moment diagrams to applying methods like moment distribution, stiffness method, and finite element analysis, interview questions often test both your theoretical knowledge and practical understanding. Are you looking to land your first career structural engineering job? Below are concise, interview-ready answers graduating engineering students can give to demonstrate the conceptual understanding expected by employers. 1. What are three fundamental requirements of structural design? Strength, serviceability, and stability. 1. Strength ensures the structure can resist factored loads without reaching material limit states such as yielding, fracture, crushing, or excessive plastic deformation. 2. Serviceability ensures deflections, vibrations, crack widths, and drift remain within acceptable limits under normal use. 3. Stability ensures the structure does not lose equilibrium through buckling, overturning, or second-order amplification effects. In summary, strength prevents material failure, stability prevents geometric instability, and serviceability prevents unacceptable performance. 2. What is the difference between determinate and indeterminate structures? A statically determinate structure has internal forces and support reactions that can be found using equilibrium equations alone. An indeterminate structure has more unknown reactions or internal forces than equilibrium equations, so compatibility of deformations and member stiffness relationships are required to determine force distribution. Indeterminate structures. Load distribution depends on relative stiffness, so modeling assumptions and member stiffness values directly affect internal forces. 3. Why would you design a structure to be indeterminate over determinate? Indeterminate structures can be designed with redundancy in structural systems. Redundancy allows alternate load paths if one member fails, improving safety and robustness. In determinate truss structures, removing a single critical member can cause collapse because there is no alternate load path. 4. What are load paths, and how can they be determined? The load path describes how forces travel from the point of application through structural members to the supports and ultimately into the foundation. Load follows stiffness. It distributes along the stiffest available path that satisfies equilibrium and compatibility. For gravity loads, this often flows downward, but for lateral or other loading, the path may be horizontal, diagonal, or even indirect. Examples: in typical steel-framed buildings under gravity loads, the load path can be roughly described as roof or floor loads transferring to beams, beams transferring to girders, girders transferring to columns, and columns transferring to the foundation and soil. Under wind or seismic loading, forces travel horizontally through floor, diaphragms to shear walls or moment frames before going down to the foundation. Noted that the load does not necessarily follow the shortest path. It follows the stiffest compatible path. 5. When does deflection control design? Deflection controls when serviceability limits, such as excessive sag, cracking, or vibration, govern before strength limits are reached. Deflection often controls in long-span beams or flexible systems like steel joists, where strength is adequate but excessive sag affects finishes or occupant comfort. 6. What causes buckling? Buckling occurs when a compression member becomes unstable due to geometric instability before reaching the material failure stress. It is governed by stiffness and slenderness. Buckling is an instability governed by stiffness and slenderness. Even if the material stress is low, a slender column can fail due to geometric instability, so I always check slenderness before assuming strength controls. Buckling occurs when the reduction in potential energy from axial shortening exceeds the increase in strain energy from bending. At the critical load, large lateral deflection can occur without additional external work. 7. What is the difference between first-order and second-order analysis? In structural engineering codes, generally first-order analysis assumes that the geometry does not change under load and ignores deformation-induced force amplification. Second-order analysis includes P large delta or P small delta effects and accounts for additional moments caused by axial forces acting on displaced geometry. P large delta effects refer to global frame sway amplification. P small delta effects refer to local member curvature amplification between supports. P large delta affects overall frame stability and drift, while P small delta affects individual member capacity and buckling behavior. In slender structures, both can significantly amplify internal moments. Ignoring second-order effects can unconservatively underestimate moments and drift in slender systems. 8. How would you determine if a structure has improper constraints resulting in instabilities? Instability can be identified by examining whether the support reactions are sufficient to prevent rigid body motion. If reaction lines are all concurrent or parallel, the structure may form a mechanism and rotate or translate as a rigid body. For example, if all reaction lines meet at one point, the structure can rotate about that point without violating equilibrium. That's a kinematic mechanism. Kinematic reasoning, such as checking for possible collapse mechanisms or rigid body modes, is often clearer than simply counting equations. A thorough analysis of velocity kinematic vector equations can be solved to determine if all speed variables are zero, indicating stability, with no mechanisms for rigid body motion. Bonus: in matrix analysis, instability appears as a singular stiffness matrix. If a structure is unstable, there exists a displacement pattern that does not require internal strain energy. The structure can deform in that displacement pattern without generating restoring forces. A singular stiffness matrix indicates the presence of a rigid body mode or mechanism. Physically, it means the structure can displace without developing internal resistance. In finite element analysis, this often appears as a zero pivot or zero or extremely small eigenvalue corresponding to a rigid body mode. 9. What is a moment connection versus a pinned connection? A pinned connection transfers axial and shear forces but provides no moment resistance. It allows relative rotation between connected members. A moment connection transfers axial force, shear, and bending moment, and restrains relative rotation so that connected members rotate together after deformation. Bonus: in reality, most connections are neither perfectly pinned nor perfectly fixed. They provide some rotational stiffness. We idealize them as pinned or moment connections depending on how stiff the connection is compared to the connected members. If the connection's rotational stiffness is small relative to the member stiffness, it behaves nearly pinned. If it's large, it behaves nearly fixed. When it's in between, we treat it as semi-rigid and account for partial moment transfer. Semi-rigid behavior affects frame drift and moment distribution. So, modeling assumptions can significantly change internal forces. 10. What is the factor of safety? The factor of safety is the ratio of capacity to demand. It provides a margin against uncertainties in loads, materials, and modeling assumptions. 11. What is compatibility in structural analysis? Compatibility ensures that deformations are consistent with the structure's geometry and boundary conditions. Connected members must deform together. 12. What is lateral load resistance and why is it important? Lateral load resistance is the system's ability to resist wind or seismic forces through frames, shear walls, or brace systems. It prevents excessive drift, instability, and collapse under horizontal loading. 13. Why would an internal pin or hinge be used instead of a rigid connection in frame design? An internal hinge releases moment and allows relative rotation between members, reducing indeterminacy and bending demand. Rigid connections restrain rotation and transfer moment, increasing stiffness, but also increasing fabrication complexity and cost. Hinges are often used to simplify detailing, reduce connection forces, accommodate thermal movement, or create a controlled plastic hinge location. 14. When would a rocker support be used instead of a roller support? A rocker support is used when large rotations are expected at the support in addition to horizontal movement. It accommodates both rotation and translation, making it suitable for long-span bridges or arches where support rotation is significant. 15. What is the difference between one-way and two-way slabs, and how are tributary loadings treated differently? A one-way slab spans primarily in one direction, so load is transferred to supports in that direction only, with tributary areas treated as rectangular strips. A two-way slab spans in both directions, and the load is shared among the surrounding supports. Tributary areas are typically divided by 45-degree lines from the corners, forming trapezoidal and triangular regions that distribute load to adjacent beams or columns based on geometry and relative stiffness. 16. Under what assumptions can we model a structure or frame as a truss? We model a structure as a truss when members primarily carry axial forces, joints are assumed pinned, and loads are applied at joints. In practice, we idealize connections as pinned when they do not provide sufficient rotational restraint relative to member stiffness, meaning bending effects are small compared to axial forces. 17. When would a three-hinged arch or tie arch be used instead of a two-hinged or fixed arch? A three-hinged arch is used when determinacy and settlement tolerance are important. A tie arch is used when horizontal thrust cannot be resisted by the foundations, so the tie carries the thrust internally rather than transferring it to the supports. 18. If your software shows an unexpectedly high moment at one node, what do? I would check boundary conditions, connectivity, load application, and mesh refinement. I would also sketch a hand calculation to verify reasonableness. Keep learning, repost to your network, and follow for more useful video. See you next.